Our final shuffle for today, I refer to it as a non-example. So what do you think that means, a non-example? Well, everything that we've been showing you in this series are Bessey shuffles. Why are they Bessey shuffles? It's because they preserve or invert Bessey sequences. That's the definition of a Bessey shuffle. I thought it important that I point out that not every systematic shuffling procedure used for small packet sizes are necessarily Bessey shuffles. Many of them are, but not all of them. And so here's an example of one that's not quite a Bessey shuffle. It actually doesn't miss it by much, but technically it doesn't preserve or invert Bessey sequences. It's called the Australian under-down. Now, if you remember, the Australian down-under, we've shown you before, and it is a Bessey sequence. That's where you have a packet of cards like this, and you put them down, and then the next one goes under, down, under, down, under, down, and so forth until all the cards have been moved. Now, the Australian under-down is almost the same, except instead of setting that first card down on the table, you place it under the other cards, and then the second card goes to the table. So let's go ahead and just illustrate the Australian under-down. So we begin with our ordered packet, as always. And so this is where you go under, down, under, down, under, down, under, down, under, down, under, down, under, down. Last one goes on top. Now, just to give a presentational insight, for the under-down deal, it's often couched in terms of she loves me, and you put the card underneath. She loves me not for the next one. That goes down to the table. She loves me, that card goes under, and you keep it. The next one, she loves me not, goes to the table. So you can use this she loves me not narrative for the Australian under-down. So let's take a look at the new ordering of the cards and see what goes wrong. So here is the new ordering. It's 1, 5, 7, 3, 8, 6, 4, 2. So in Cauchy's two-line notation, we obtain the following. The top row is always 1 through 8. And now we get 1, 5, 7, 3, 8, 6, 4, 2. Converting this to cycle notation, we obtain the following. 1 gets sent to 1, so it's a fixed point. It's also called a 1 cycle. What about 2? 2 gets sent to 5, so we have an arrow from 2 to 5. 5 goes to 8, so we have an arrow from 5 to 8. 8 goes back to 2, so it cycles around, completing a 3 cycle, is what we call it. What about the value 3? 3 goes to 7, so we have an arrow from 3 to 7. 7 goes to 4, so we have an arrow from 7 to 4. And then 4 wraps around to 3, so that completes a second 3 cycle. And then we see that 6 goes to 6, so we have a second and final fixed point. It's also called a 1 cycle. Now, it's when we color code these that we discover that we have a problem. So let me just remind you of our color coding system. And the reason for it, of course, is so that we can see what the shuffle is doing to the structure of Bessey sequences of order 8. So recall, position values 1, 4, 6, 7 are color-coded black. Position values 2, 3, 5, 8 are color-coded red. Okay, so let's just see what happens here. So we see that black 1 goes to black 1. That's fine. Red 2 goes to 5, which goes to red 8, which wraps around to red 2. Now, so far, given just that much information, we're not in trouble. It looks like if it's going to work out at all, it looks like this shuffle will preserve Bessey sequences, meaning the cards that originally began in positions 1, 4, 6, 7 stay somewhere within those positions, and cards that originally began in positions 2, 3, 5, 8 stay within those positions. So far we're fine. When we go on to the second 3 cycle, that things fall apart. So let's take a look at this. We see that red 3 goes to black 7. Right there, that's a problem. Because right now, for it to work, all of the black position values need to go to black position values, and all of the red position values need to go to red position values. And if that happens, the Bessey sequence form has been preserved. Well, we have a problem here because we have a red position value, namely 3, being sent to a black position value, namely 7, and then that black position value 7 is being sent to 4, and then once again we have a black position value, namely 4, being sent to a red position value. Okay, that's a problem. In fact, this just by itself is an indication that the shuffle that has a 3 cycle like this cannot be a Bessey shuffle, because we either need the same color values being sent to themselves, or the value of one color has to be sent to a value of the opposite color. Okay, and that's not happening right here. In fact, if we get rid of this entirely, if this is gone, then what's left is fine. It seems to be preserving things. It's this second 3 cycle that ruins it. Okay, and now why don't we illustrate that this in fact goes wrong with our quintessential Bessey sequence 1 0 0 1 0 1 1 0. And then I note down here, Bessey sequences are neither preserved nor inverted by the Australian under-down. Okay, so why don't we go ahead and just show you that our Bessey sequence structure is neither preserved nor inverted. It's actually destroyed. So here I'm beginning with 1 0 0 1 0 1 1 0. Let's go ahead and perform this under-down. Maybe this time we'll use the she loves me not narrative. Okay, so she loves me not. She loves me not. Yes, no, yes, no, yes, no, yes, no, yes, no, yes. Okay, what is the new sequence structure of our packet? Well, let's take a look. Oh, we haven't seen this before. Why is that? Because it's not a Bessey sequence. This part right here is fine. You know, this could be part of one right here. So 0 1 1 0, that's fine. And then we would need to have, for this to complete a Bessey sequence, we would need to have a 1 0 0 here and a 1 there. So if these two right here, if these two cards were to just switch places, it works just fine. That would actually now be a Bessey sequence if these two were to switch. So we're kind of just barely missing it by a single transposition of 2 cards. 2 neighboring cards just need to be switched for this shuffle to preserve Bessey sequences. But since it doesn't, we can see that indeed our Bessey sequence structure has been destroyed. Okay, so that's why I call it a non-example. It's a sequence that doesn't quite work. Now what's interesting is in some ways it almost works. It's not that far off. So let's take a look at the shuffle diagram for our non-example here, the Australian under-down. So we have a 3 cycle 2 5 8. So we would expect to see an arrow from 2 to 5, which we do, and then an arrow from 5 to 8, and then an arrow from 8 back to 2. And that completes that 3 cycle. And notice that all of those vertices, 2, 5, 8, are color-coded red. So that's a little 3 cycle. Those 3 values also constitute an orbit. And in some ways, they're not harming the preservation of a Bessey sequence. It's when we get to the second 3 cycle. So we see that 3 goes to 7, which goes to 4, which wraps around to 3. So if we start at 3, we should see an arrow from 3 to 7. But unfortunately, it's red, 3 to black 7. And then we have an arrow from black 7 to black 4. And then an arrow from black 4 to red 3. Okay, so that is not going to preserve 1001, 0110, or its inversion 0110, 1001. Both of those will be destroyed by this Australian underdown. Okay, so let's go ahead and show you a final application for this series on Bessey shuffle diagrams. Now, the last application I gave you was quite advanced. So I thought we would bring it down a few notches so that we don't lose too many people. So let me just show you a really fun application. And what I thought we would do too is, since we're at the end of this series, we can draw from any of the shuffles, except of course this non-example here, any of the previous shuffles, 1 through 47, to mix the packet and then finish in the way that we would like to.